Hello, this is Theresa Stack. I'm an associate professor for Montana Tech, and this learning unit will cover exposure assessment. More specifically, we'll review calculating concentrations, time-weighted averages, some exposure evaluations based on OSHA compliance, where we use confidence limits and standard analytical errors to run our exposure evaluation. So some steps in evaluating somebody's exposure to an occupational exposure limit would be, after sampling, of course, to calculate the time-weighted average for the similar exposure group, or calculate the actual time-weighted average for each person. In the on-campus lab that you'll attend in June, we'll talk more specifically about using a program called IH Stats or IH Statistics and log transforming your data. Most occupational exposure data is log normally distributed, and you need to transform it before you can calculate a time-weighted average or put confidence intervals onto it. We will not cover this here. We're just going to use straight time-weighted averages and mean type calculations. We'll talk about log transformation elsewhere. So first, your time-weighted average. If you've collected enough samples, and you certainly should, evaluate your short-term exposure limits. There should be no more than 4 15-minute short-term exposure limits per shift. And of course, the time-weighted average can never be exceeded. You can also evaluate an action limit or an excursion limit, which is your action limit is half of your PEL typically. Sometimes other occupational exposure limits exist, but it is a good starting point. And then we take our time-weighted average and we calculate a severity with our standard analytical errors on it. So many different ways in which we can evaluate exposure. So briefly to recap, your time-weighted average, half of the PEL to look at whether you've exceeded an action limit or not, and then we could look at our severity and put confidence intervals on them with our standard analytical errors. So our first review is how we calculate a concentration. And a concentration is quite simply the mass or the weight of the contaminant that we collected over the volume of air that we drew through the pump. So now you can see how important it is to send the right air volume to the lab, or neither you or them will calculate the concentration accurately. So let's take a look at some lab results. We sampled on April 15th. The lab received the samples on April 18th and analyzed them on April 25th. They analyzed the sample using NIOSH method 0600 for respirable dust. They found a mass in milligrams of 0.37 on the filter, and they found a concentration, which would be the mass over the volume, of 0.31 milligrams per meters cubed. So let's just take a look at this, and I hope you could note why it's so important for this sample volume to be accurate, because it's used to calculate our concentration. Of course, whatever our sample volume is will affect our concentration, and that's why we have to be very particular about the sample volume in liters that we send to the lab, so that we don't make an error. So it looks like we drew liters, and I'm going to multiply this by 0.001 meters cubed per liter, and our liters will cancel out. and that'll give me a sample volume of 1.21 meters cubed. I'm only using 2 significant digits here because we only have 2 significant digits here. It will change your calculations depending on how many significant digits you use. And so now our mass of our sample is here in milligrams, 0.37 milligrams. And when I place this over my sample volume and I do the math, I'll get 0.37 divided by 1.21, and that'll give me 0.3058 milligrams per meters cubed. And you can see that they rounded up. So a time-weighted average is the average exposure for an individual over a working period of time as determined by taking one or more samples of the same contaminant during the work shift. And our calculation for a time-weighted average is concentration, or more specifically, it's the sum of concentration times time divided by the sum of time. And again, this isn't the 8-hour time-weighted average, this is the actual time-weighted average. That is what is being used here. And we use this a lot in the class because we're talking about airborne concentrations. So now let's do a sample together. Okay, well let's evaluate an exposure by calculating a actual time-weighted average. First, we'll take our sample volume and calculate it in liters, convert it to meters cubed, and then we can get our concentration, and finally calculate our time-weighted average. So I'll just let this row be for column A, this row be for column B. So we have our Q equals volume over time. And that is our first formula. So our flow for A is 2.204. That equals some volume over time. And for B, we have and that equals some volume over time. And then I can calculate it in liters and calculate it in meters cubed. So first I'll start here. So there is my answer in liters, and if I multiply it by 0.001, I can get my conversion of 0.529 meters cubed for sample A. Sample B, and again I'll multiply it by 0.001 and do my conversion. I got 0.6077. Now our concentration formula is right here. So my concentration will be 3.005 divided by 0.529. I have 2.457 divided by 0.6077. So now I've calculated my concentration for both of my samples. If these were taken separately, our PEL is 5.2. Our first sample was above, our second sample was below. But since this was a continuous sample, we took two separate samples, but we're going to evaluate it together. Let's evaluate our time-weighted average, which our formula is, it's the sum of concentration times time over the sum of time. So I have my concentration times time plus my concentration times time which is my sum of time. I added these together. So let's see what our time-weighted average is. Now we have our time-weighted average. So we've done our sample problem to calculate a time-weighted average, and now we're going to look at evaluating an exposure with 95% confidence. And this is out of the OSHA technical manual, so it's the way a compliance officer would do it, and I think it's important for you to understand the error bars on our sampling. So in our post-sampling evaluation, OSHA directs us or advises us to analyze our results by using our sampling analytical errors. And there are variations from the actual truth from the actual true exposure due to sampling errors and analytical errors. And analytical errors are those errors that are in the methodology that they're using, as well as the equipment and the calibration of the equipment which is being used to evaluate your results. So all these things, the times when we start and stop a pump, variations in the flow rate of a pump, errors when we're wrapping up our samples, and then also errors that are caused by the laboratory itself and their analytical equipment, we can take those into account to be more confident of our exposure evaluation. So when an employee is sampled and the results are analyzed, the measured exposure will rarely be the same as the true exposure. Standard analytical errors are used to place confidence intervals on permissible exposure limit or occupational exposure limit assessments. And honestly, the true error depends on a combination of effects. So standard analytical errors represent 95% confidence limits. We get the standard analytical error from the lab. Usually you have to request it. And again, it's due to variations in lab equipment's ability to accurately and precisely measure the sample amount, which is usually the sample mass. And so this is really important when you're using data that we considered censored data, such as data that's right there at the limit of detection or the limit of quantification. And I hope that one thing that you realize is that lab equipment itself has got some errors related to it, some variability, and we need to understand that variability so that we take that into account when we're evaluating a person's exposure. So the OSHA technical manual link is right there. You can find it under post-inspection activities. And so I have this symbol here just so you can recognize that the triangle represents our time-weighted average or our concentration if it's only one sample. And then our upper bar is our upper confidence limit, and our lower bar is our lower confidence limit. And to look at this in an overview, our standard analytical errors are like our standard deviation or confidence limits applied to our time-weighted average. And they're used to compare our results to the occupational exposure limit. So here, if we have our, you can see this is your time-weighted average. The lower confidence limit is above the occupational exposure limit. We are 95% confident that there is an overexposure, that we are non-compliant. When we have, again, our time-weighted average is our triangle, and our upper confidence limit now is below our occupational exposure limit or below 1, we can be confident that we are in compliance, that our exposure that we measured is below our occupational exposure limit. Where we're unsure of whether an overexposure exists or not is when we have our lower confidence limit falling below 1 or falling below our occupational exposure limit. So in this example, our time-weighted average would have come out above our occupational exposure limit, just like we saw in our example that we did together. Our time-weighted average was 5.5, our PEL is 5.2. But how confident are we that what we measured is actually above our permissible exposure limit? Now our upper confidence limit is of course above our occupational exposure limit, but our lower confidence limit was below. So we're really unsure of what the true measurement was. And this is the one where we're more likely to make a mistake because our time-weighted average would have come out below the occupational exposure limit. And when we put our standard analytical errors onto our time-weighted average, we can see that the upper confidence limit came out above 1 or above the OEL. And now we have a possible overexposure. This is the one that people are most likely to make the error on, and we'll do some math so you can further understand it, but I think this visual representation kind of starts to get us anchored. So a definition of a confidence limit from the OSHA Technical Manual are error factors determined statistically shall be applied to sample results to obtain with some degree of confidence the upper confidence limit, which is the highest value the true exposure could be, or the lower confidence limit, which is the lowest value that the true exposure can be. So here we can see when our lower confidence limit and our upper confidence limit are both greater than 1 or greater than the OEL, we are 95% confident that what we measured is a worker's exposure above the occupational exposure limit. So our time-weighted average with 95% confidence is above our occupational exposure limit. So in our second scenario, we have our upper confidence limit is below 1 or below our occupational exposure limit. And if our upper is, of course our lower is. And now we're 95% confident based on the measurements that we took that the worker's exposure is below the standard or below the occupational exposure limit. And again, these are the two that are more difficult to interpret. Because here in this scenario, your time-weighted average would be above your OEL, but because your lower confidence limit is below the OEL, you really aren't certain if somebody's overexposed or not. And that's because there's errors associated with our sampling, and there's errors in precision associated with the laboratory equipment itself. And again, here's the one where we're most likely to make an error, is where we have our time-weighted average below our OEL, and if we strictly interpreted it, we may believe that a worker was in compliance. But when we put our confidence limits or our confidence intervals on our time-weighted average, we would find that our upper confidence limit is actually above 1, above our OEL, and therefore the workers may be overexposed. And I believe when we do the math, this will make a little bit more sense to you. So So our confidence limits are fairly straightforward and easy to calculate, and these are used for full period continuous samples. So that's just one sample over an entire work shift. If we have multiple samples, we use a different calculation, one that's a little bit more complicated, but we'll start here. And so although X is the concentration, if you only have one sample, the concentration becomes the time-weighted average. It necessarily is the same. So our first step is we calculate the severity, which is your time-weighted average divided by the PEL. And then you calculate your lower and your upper confidence intervals by subtracting and adding the standard analytical error to your severity. And we use 1 as our starting point because if you had a time-weighted average of 1 and you divided it by a PEL of 1, you would get 1. Or if you had a time-weighted average of 6 and you divided it by a PEL of 6, you would get 1, right? Your severity would be 100%. People would be at 100% of their limit. So we use 1 because that's the ratio. If your Y is less than 1, then people are below the permissible exposure limit. If your Y is greater than 1, then people are above your permissible exposure limit. So what is the determination if you have a possible overexposure? It's that a violation is not established, but it is possible. As the lower confidence limit comes closer to the PEL, as your lower confidence limit comes closer to the PEL, the more likelihood that a person would be overexposed. Exposure may be there, but you may not have sufficient documentation to be out of compliance, and therefore you need to perform another calculation. So first we start with a basic calculation, and then we go on to a more advanced calculation. This is when we have this possible overexposure. I mean, if it's clear cut, we put our standard analytical errors on there and we get values, our upper confidence limit being less than 1, then we know that people are safe. When we get our lower confidence limit being greater than 1, then we know people are overexposed. It's when we have this split between that line that we're not quite sure of. So we should consider further sampling depending on the seriousness of the hazard or the agent that people are exposed to. Also consider resampling if there's citations or if you are close to the PEL, or if the time-weighted average is half of the PEL and you're at your action limit. And certainly we're going to try to always encourage our employers to sample when we're just not confident based on our confidence intervals. So we have our sample data here that we have previously calculated. We calculated our concentrations. And now let's just use this fun little formula to evaluate the exposure or not based on the upper and lower confidence limits or confidence intervals. So I have my standard analytical error from the lab is 0.2. The PEL of my agent is 5.2. My first concentration was 5.68 and my second concentration was 4.431. Okay, so we're going to start with, again, I'll put sample A here on the top, sample B on the bottom. So our severity is our concentration over our permissible exposure limit. So our concentration is 5.68 divided by 5.2, and our concentration for B was 4.431 divided by 5.2. So our severity is 1.09. For sample A, and for sample B, it's 0.852. So you can see when we did our comparison that sample A is 109% of the PEL, and sample B is 85% of the PEL. Because that's truly what our severity is. It's our concentration over our PEL, so it's just a simple ratio. Now let's calculate our upper and our lower exposure limit using our standard analytical errors. So I have 1.09 plus 0.2. 0.2 is given from the lab. So in this situation, I am, my upper confidence limit is above 1 and my lower confidence limit is below 1. A possible overexposure may actually exist. Now let's calculate the second sample. Our severity was 0.852. And again, we have the same situation. Our upper confidence limit is greater than 1 and our lower confidence limit is less than 1. So there's a possible overexposure. So what this would look like graphically, remember our OEL equals 1. And in our first situation, the concentration was above 1. Our upper confidence is above, but our lower confidence is below. In our second situation, our concentration was actually less than our permissible exposure limit. It was less than 1. So it was down here. Our upper is above and our lower is below. So here we have some possible overexposures, and therefore we need to evaluate them more specifically. We can also use this next calculation if we want to combine multiple samples. So here again is, I put some numbers in so you can see that the OEL is 1. Our severity was 0.85 because our sample was less than the occupational exposure limit, which was 5.2, the OEL in this example. Our lower confidence limit is below, but our upper confidence limit is above. So we have a possible overexposure. This is one, like this is one, that we could have missed if we just took the concentration at face value. So what we need to do is, our overexposure is plausible, but we need to do a more in-depth calculation. So we can use this calculation for when we have the situation that we do. We have a possible overexposure. We can also use this calculation when we have multiple samples, and so I'm using it to show you both. In this calculation, we only need to calculate the lower confidence limit. We don't need to calculate the upper confidence limit. So again, it looks somewhat complicated. What I warn you to be careful about is you need to do the entire top first, then divide by the bottom, and subtract out your y here. And when you're doing the more specific standard analytical error calculation, your y here is your time-weighted average divided by your PEL. And that makes sense because you have multiple samples, but I think it could become slightly confusing. So let's do an example together. Okay, so we have our setup here, and that's probably what's most important, is to get our setup right. So let's start by calculating our severity. Again, we're going to use, this is our time-weighted average, so it's our time-weighted average of these two together, which we've already previously calculated. Our severity is our time-weighted average divided by our PEL, which gives us a severity of 1.057. So our severity is 1.057 minus our standard analytical error, which is 0.2. Again, we got that from the lab. And now we take the square root of time times concentration plus time squared times concentration. And we'll put this over the PEL times our sum of time, which is 450. Okay, so in the grand scheme of things, this is all just a big giant math problem. Just ensure that you do the entire top first before we do our subtraction. That seems to be where most people make their errors. We already got our severity. So I'm just going to start to put this in the calculator, and hopefully you can see where I'm going with this. It's slightly difficult. Hopefully I'm doing a pretty decent job. So okay, let's put this right here, and I can see the best, and you can see too. So I'm going to start with our calculation of 240 squared times 5.68 squared, close parentheses, plus we have our 210 squared plus our 4.431 squared, and I close those parentheses. And I've done this inner value here. And now I take 0.2 times the square root of my answer, and I'm able to get this upper number, 275.85. So I have over divided by the PEL times the sum of time, and this will give me 1.057 minus 0.1179. This is my lower confidence limit. So I take 1.057, which is our severity. I'm going to subtract that from this calculated value. Gives me an answer of 0.9391. Because our lower confidence limit fell below 1, fell below the line, I can be 95% confident that the person is in compliant. They are not overexposed. And that's by using our standard analytical errors, calculation for multiple samples, and being very specific about weighting it by time and against the permissible exposure limit. So truly what you're doing is weighting each part of this sample as a ratio against your permissible exposure limit. There's your setup in our evaluation. It's confirmed. So, in summary, the main purpose of sampling is to measure contaminants for the protection of workers, but believe that there are errors inherent in the process no matter how careful we are, and that there are errors in the analytical methods no matter how precise the lab may be, and that they can report to you their standard analytical errors. For OSHA compliance, both that upper and that lower confidence limit need to be above 1 or need to be above the occupational exposure limit, but you can use this as you evaluate exposures as an industrial hygienist when you have values that are close to being within compliance or outside of compliance. And so these confidence intervals represent a 95% confidence in our ability to evaluate somebody's exposure. And this is the screenshot from the OSHA technical manual, and you can find all the links there if you wanted to go back through and take a look at some of those calculations. Thank you very much.